you are having a 48 volt grid here, then it can be stepped down to 12 volts. So this can supply, if you need a 12 volt load, directly can be connected here, as well as if the load requirement is further down to 5 volts, you can still go to still place another set of DC-DC converters to bring it down to 5 volts. So effectively, if we see what are the advantages of going with this, is the standardized design, ease of customizing. This is very important because based on the your capacity, you can either increase or decrease the power availability. You can, if you have more affordability, you can at a later stage also add solar photovoltaic, or initially if you have set up a solar photovoltaic plant, you can add up a small wind turbine. Maintainability is easy. It's not connected with the grid, so a lot of issues that arise due to the interfacing, synchronization, etc. are washed off. Packaging of those converters become easy for distribution. Otherwise, you would have to go for a large thing. Power density is also increased, and the reliability, of course, goes up. So as a result, distributed system, if you go, these are the advantages, and also these throw a challenge that if you want to design a good converter or a good distributed power system, you need to have the system which fulfills all these requirements, which are of course their advantages. Other features are scalability, redundancy, modularity, fault tolerance, capacity. These are additional features that depending on the customization can also be obtained. So if you see what are the general requirements for a DPS, distributed power supply system, you need to have regulated output, either it be 48 volt, 12 volt, 5 volt, or even 1.5 volt. Nowadays, the trend is that everybody wants that the power should be available at as low voltage as possible, but which becomes more challenging as a power electronic engineers for us, that if you supply power at 1.5 volt, and that becomes much challenging when your current capacity is quite increased. So one very good example that comes clearly depicts this picture is that we all are aware about the Intel processors, which you say that core i7, core i5, and these are 7th, 8th, 9th, 10th generation processors are there. So gradually, if you sometimes pick up the data sheet of any of these processors, you will find that these operate at a very low voltage of somewhere around sometimes 3 volts, or sometimes even 1.5 to 2 volts. And can you just imagine what is the current capacity they must be requiring? If you just think when I discuss this particular thing during face-to-face talk, generally what I get answers is something like a few milliamperes, sometimes 1 or 2 amperes, but no. As of this three or this statistics, what I have seen was 3 to 4 years old. That time it used to be 40 amperes at 1.5 volts. So you can imagine that the power requirement and that supplying 40 amperes current at 1.5 volt is really challenging, and that too you need to regulate. So once the voltage level is say 1.5 volt or 3 volts, the regulation becomes more tough. If you are regulating at 100 volt or 48 volt, even 5% fluctuation is quite bearable, but it's not in case when the voltage levels are quite low. So you need to have high power density, precise, wide range, and fast control, together with high efficiency. And another important thing that we should not miss is about low electromagnetic interferences. Sometimes if the power processing level is high, you also need to go for isolations and multiple outputs. So multiple outputs, earlier there was only the understanding that if you want to have multiple output, you need to go for isolated DC-DC converters, which require galvanic isolation, thereby increasing the weight and lot of other issues. But now there are many multi-port DC-DC converters that have also been evolved, although I have not covered that in my presentation for now. But there are several multi-port DC-DC converters which are quite suitable for such applications where you have multiple energy sources with single or two outputs. So then these non-isolated part I have discussed. Other resonant converters are also there, which improves the efficiency. But let us talk of only the non-isolated converters. Conventionally, we are quite familiar and comfortable with your second order DC-DC converters, which are your buck converter, boost converter, buck boost converter. And even there are some higher order DC-DC converters which are quite popular and well reported in several books, and most of you must have come across these converters are Cuck converter, Sapik converter, Zeta converter, and many more. So why I say them is I classify them as a second order and higher order is, if you recall and look at the structure of a conventional buck converter, boost converter, you'll find that it has one inductor and one capacitor. So ultimately it has only two energy storage elements, and these two energy storage elements contribute to each order. So if you convert a transfer function, if you make the transfer function for these converters, you will find out that the small signal transfer function will have a denominator which has a maximum power of 2, s to the power 2. So that indicates that your converter is a second order converter. But there are a lot of restrictions, limitations in terms of the steady state response, which I'll discuss in the coming slides. And to overcome that, you need to increase the excuse me, you need to increase the number of energy storage elements. And once you increase the number of energy storage elements, it helps you in improving the performance. But together it comes with some other limitations. So there needs to be a trade-off design that also I'll be discussing shortly. So my focus for today's talk will be on fourth order boost converter topologies, mainly on boost converter topologies, because mostly when you are integrating the renewable energy sources which have low power generation, the generated voltage is of lower magnitude, somewhere around 20 volts, 24 volts. So when you interface them with a DC grid, you need to boost the voltage. So four types of DC-DC, fourth order DC-DC converters I'll be talking about. I'm naming them as, although they both are, all are having four energy storage elements, but their properties and the steady state characteristics are quite different from each other. And interestingly, once I move to the further slides, you will find that these converters are obtained using one single conventional converter just by interchanging the positions. So the formation of these converters is quite interesting. These are the some of the advantages of higher order converters. Of this, if you see, important is low inductance and capacitance requirement. So even though we are increasing the number of energy storage elements, but still the overall requirement of inductance and capacitance will be reduced. Second important thing is the continuous source and the load current. So this is again second important thing. So a very quick discussion on why you need continuous source and load currents. So this continuous source and load current is important for us because it increases the life of the solar panel and also the life of the storage thing. So if you see the waveforms of which I'll also show in the coming slides, if you see the waveform of the normal conventional boost converter, you will find that the current is discontinuous in nature, and as a result, if you draw a rippled current out of a battery, it's going to reduce its life. So this is a conventional DC-DC converter which you are quite familiar with, and the gain is 1 by 1 minus D, where D is your duty ratio, V naught is the output voltage, Vg is the source voltage. So and the second figure shows again a DC conventional DC boost converter, but here if you see I have added a capacitor and an inductor with the aim of improving the performance of the steady state performance of the converter. So if you look here, you will see that there is a diode placed which gets switched on and off at a regular interval. So once this diode is off, the current ICR is going to be zero, and as a result the current which is going towards the load is going to have high peak to peak ripple. In at one time that current will be zero, and at other time that current will be equal to the load current plus the ripple. So this discontinuity deteriorates the life of the load as well as it's not desired. So you include a filter again, an LC filter is included so that the placement of this inductor makes the current ICR continuous, thereby improving its performance. So this is what you see, that this is the discontinuous nature of the ICR current, which was creating the problem. At one time it is zero, at other time it is having taking a high value, which is now by placing of the traditional filter has become continuous. So taking that topology, the four topologies that are framed are as shown. This is the first topology which is obtained by changing the locations and the connections of the DC the for boost converter with filters. So here you see that there is an inductor which is placed at the load side, and this is your intermittent inductor, and a capacitor is placed in between. So this capacitor plays an important role in the power processing or the power boosting and transfer from source to the load. So the second converter, if you see, it is formed by interchanging the by changing the position of the inductor, which here was at load side. Now this inductor is now placed at the source side. So only one change is done, and this changes the characteristics. So you have the possibility of placing it at the load side, or you have the possibility of placing it at the source side. Next converter which is formed is from this TIBDC. Here if you recall that the source inductor is maintained there as well, so this conductor is inductor is kept here, but what is changed is the position of the capacitor and the diodes are interchanged. In this case this was the position, but here the position is interchanged, and also the position of the switch as well as the MOSFET as well as the inductor is, or second inductor is changed. So by changing this position you are able to obtain another set of another topology for a boost converter. As the number of energy storage elements is still 4, the order has not changed. Another converter which can be formed is from the first converter. Here you are interchanging the position again of an inductor and the diode, and here you are changing the position of switch and the capacitor. So similarly there are many other permutation combinations which are possible, but what you need to see is that all these permutation combinations may not be a working solution. So you need to see that although we can randomly place all these switches and the inductors, capacitors, but you need to work out do sufficient analysis so that you can establish that that is a working converter. Not only a working converter, even if you are able to frame a working converter, it may not necessarily give you an improved performance. So that also need to be checked out. So the HRFOBC, the fourth converter that I talked, uh, although it's a fourth order converter obtained by interchanging the position of the same converters and the switches, but later we will see that this do not offer improved steady state performance, rather it deteriorates the performance. So it's not always that the higher order, increasing the order will improve the performance. Moreover, increasing the number of inductors, if you have eventually landed up in increasing the magnetics, increasing the higher value, putting up the higher value of the inductors and the capacitors, it will slow down the dynamic response of the converter. So at one end it increases the steady state response, but on the other end it reduces, because it goes up with the simple theory that if higher the value of the inductor do not allow sudden change in the current. So if you want to change the load suddenly, then the magnitude of the load has to change instantly. But if you have placed a large magnitude inductor, then it won't allow you to instantly change. It will have its own time constant, and slowly only it will allow the current to change. So higher magnitude of the inductance or the capacitance will lead to slower response. But on the other hand, if you remove them completely or reduce these, the steady state will be affected. So there need to be a trade-off in the design, what you want. So you have to compromise with one or the other thing. So this first converter operates in two modes, mode 1 and mode 2. These are the equivalent circuits which which needs to be drawn for the further analysis. And this is the waveform which is seen, and you see that the source current here, Ig, inductor currents, they all are continuous in nature. Also ICR, because of the presence of this inductor, ICR is also continuous in nature, as against the red dotted line which shows your ICR of a conventional boost converter. So this is how you could improve. And also you can see the waveform of the voltage. What you see is that the load voltage shape was having higher ripples, hence higher EMIs in case of your conventional boost converter. But in this case, you have a continuous load voltage which is desired. So by adding one inductor and a capacitor, you could drastically improve the load side performance of your conventional boost converter. This is state space analysis for developing small signal model. I'm skipping this. I have not included also in the presentation because it's quite too mathematical thing, and it's not required also for understanding the present topic. So this is the second converter. Again, the two modes of operation are there. One case switch is on, diode is off. And again, a lot steady state time domain analysis can be carried out, which tells that the waveforms for this as well are continuous in nature. They are having continuous source ICR current as well as load current. Further, this has some interesting features as well. So what you can see is if you see the equivalent circuit for both the inductors, for both the modes of operation, you see that in both the cases, if you apply Kirchhoff's current law at this junction or at this node, you will see that the current inductor current is getting divided into two. So you can write that ICR, we are interested in the current which flows towards the load mainly. It depends on IL1 and IL2. And if you differentiate it, you find that dIL1 by dt, which is the peak to peak ripple, this is which indicates the slope of your inductor current. This indicates the slope of your inductor current too. And if you multiply it with time, you find the peak to peak ripple. So you can establish a mathematical expression that the peak to peak ripple in the load side current, this current ICR, is equal to delta IL1 minus delta IL2. So ideally what you want is that the current which is flowing towards the load should be a ripple free current, and as a result it should be a pure DC ripple free current. And if that happens, then the filtering requirement can be eliminated. So you have a possibility that you can eliminate this capacitor, or if not eliminate, you can drastically reduce the value of this capacitor. So how you can reduce this delta ICR is, if you maintain delta IC1 delta IL1 constant, then this can be reduced by increasing the magnitude of delta IL2, and that can be increased by decreasing the magnitude of the inductance, as the ripple, peak to peak ripple, is inversely proportional to the magnitude of inductance. So if you want this ripple to be high, you can reduce the magnitude of the inductance that you are placing. So the reduction in the magnitude is good for us from our design point, because it is reducing the size, it is reducing the bulkiness of the converter. And moreover, uh, why we go for a high value is so that the ripples are reduced. But here you can see that since this is the intermediate inductor, even if you increase its peak to peak ripple, it is helping you out in reducing this. So not only you are able to reduce the magnitude of the inductor L2, you are also able to reduce the filtering requirement. So this is the plot which shows the peak to peak ripple against variation in the both the currents, both the inductances, and you find that as you keep on decreasing the magnitude of the inductance, the peak to peak ripple also keeps on decreasing, and at certain point it acts as a conventional boost converter and ripple increases. So you have to find out this optimized point, which is also seen here, that it keeps on decreasing, it reaches some minimum point and again it shoots up. So you need to design the value somewhere in this range to attain the maximum benefit. Now this is the fourth converter which I had included there. Here what you can see is, although it's a fourth order converter, but the delta ICR is, its shape is discontinuous in nature. So what is visible here is that although we are increasing the magnetics, although we are increasing the order, compromising with many other things, but still it is not able to give you an improved response. As against it, you can also see the load voltage, which is having very high ripples. So this has high ripple at the source side, and this is the source current, so which also you see earlier, which was quite continuous in nature. This is having, so this converter, although it's formed, it is working, it works fine as a boost converter, but it is not offering any benefit. So developing such type of converters and analyzing is not that beneficial, because it will anyhow deteriorate all your performance parameters. Then this is the third converter which I have discussed here. So in this again you see that the placement is such that in this case, although you are getting a high ripple at the load side, since the discontinuity is arising, but the source current ripple becomes almost DC. The source current ripple is almost zero in this case, comes out somewhere around 1 to 2%. So this converter, although it's not improving the performance of the load side, but it drastically improves the converter performance on the source side. So interestingly, what happens is, in the first two converters you were able to see that it was improving source as well as load side performance, but this converter, the previous converter, was not at all suitable, but this converter not suitable from the load side aspects, but it's quite beneficial in terms of interfacing the either battery as a input or the solar panel as an input. These are the, after performing some mathematical analysis, these are the mathematical expressions for various voltages and currents. Then you have the design equations, that what should be the magnitude of the inductance and capacitance, how you will design them. And this is taking some 50-watt power I have designed, what are the different values. So interestingly, if you see that the peak to peak ripple or the load voltage ripple is important. So here if you see that the load voltage ripples vary, in a conventional boost converter it was 1.1, somewhere 1%, but in other two converters it was quite low, 0.068 and 0.055. In the third converter, which was not suitable, again it was high, and also in the fourth converter it was high. If you talk of the ICR, boost converter is discontinuous in nature, whereas other converters, FOBC1 and FOBC2, this are giving relatively far less peak to peak ripple as compared to the conventional converter, and also as compared to the other two higher order converters. So in this case, if you see that to attain this, inductance requirement was only 125 microhenry for L1 and 8 microhenry for L2, and that too with this small inductance we are able to attain a peak to peak ripple which is less than 20%, which is the standard. Now if you want to attain and see this, if you have such a large ripple, then you need a very large filter capacitor to filter it out, eventually increasing the size and weight. You see the pulsating current in the source side, the current is pulsating in nature, but here it is continuous in nature. But if you see that uh, if you want to attain this same ripple of 2.95%, which I mentioned that this is the advantage of your fourth converter, which says that the ripple is only 3%. If you want to attain it with this converter, you need to have a conventional boost converter. You would have required a capacitance of 700 microhenry, which means a sluggish dynamic response because the inductance is quite high. If you want to attain it using FOBC1, then also you need both the inductance to be 700 microhenry, with FOBC2 400 microhenry, and with this not at all possible because of very high ripples. So ultimately, depending on the requirement, you choose these converters. This is the direct one-on-one comparison of the load voltage waveforms of all the 4 converters. This is for the load current comparison, how the shapes which we have already discussed in the previous slides. And source current comparison, you can see here that as compared to other converters, the red one, which is your LSCR BC, the fourth converter, which was having very less ripple, and this one is for the converter which is not suitable, even belonging to higher order converter class. Then this is again the continuous and discontinuous nature of the currents comparison, which we have already covered up now. This shows the FFT analysis, which shows that if your peak to peak ripple is high, then it will lead to larger EMIs, and the harmonic content is high. So you can see the FS, 2FS and 3FS components are increasing in although magnitude is decreasing, but they have higher harmonics present in the system, and eventually they are contributing to increased EMI. So this is for the FFT for the load side current. This is the FFT for the load voltage, which is quite less as compared to the currents. This is the data compiled from the previous figures. This is the comparison, so which clearly shows that for some of the converters which have high peak, they are not too useful for us. This figure talks about the stress comparison. So you see that the switch voltage stresses and diode voltage stresses are almost comparable. They are almost same. So even we are increasing the number of energy storage elements, we are not compromising with our switching requirements are not device requirements are not going up. Same switches which were used for conventional converters are still suitable. Same for the current stresses. You see the current stresses and the switch as well as diode are almost comparable. So this can be easily handled with the conventional IRF 540 or MUR 860 MOSFETs and diodes respectively. So this can be easily handled. So those converters have been also tested experimentally, and which shows that whatever we have discussed are in close confirmations. Your ripples are the nature of the current is similar. The waveforms are continuous in nature. So this is for the other 2 converters. This shows the experimental result for the change in the source current ripple comparison against increase in the duty ratio. So as you are increasing the duty ratio, ripple content is further going down. So it again depends on at what voltage levels you want to operate your converter. Then you have these are the inferences of this. We have already seen that which converters are suitable, which converters are not suitable. So that's it. Then comes the design and the dynamic characterization. So in this we can see the general dynamic representation converter appears something like this. So I'd like to just interrupt and ask Professor Manish, we have sufficient time is available with us now. Can I continue? Manish sir?
Sir.
Sir, do we have time? Can we continue?
Yeah, you can continue, please. We have time.
Okay, thank you. So if you talk of the small signal models that are developed, these can be represented in this metric form, which tells the dynamics of the source, the load voltage V0 and the dynamics of the source current IG. So this is the block diagram, a small signal block diagram, which represents the load voltage dynamics, that which indicates that your load voltage is affected, or it depends on three small signal transfer functions, which is the control to output transfer function GVD of Z, audio susceptibility GVG of Z, and output impedance Z naught of Z. So the Z is, these transfer functions are indicated in discrete time, which depends on the duty ratio, source voltage, and the load current. Similarly, you have source current dynamics, and these source current dynamics, these are again interrelated with three different transfer functions, thereby affecting the dynamics of the source current. The together control diagram looks something like this, with a, which is a voltage mode or single loop control diagram, which appears like this indicates the output voltage dynamics, which we have just seen. And if you connect it, if you close the loop, you have the sensor reference voltage, then the controller and the PWM modulator. So this forms the closed loop control block diagram for single loop control. These are the formulas which are derived used by solving the block diagram reduction to obtain the different closed loop transfer functions. So this is how you obtain the open loop transfer functions, and this is how you obtain the closed loop transfer functions. So all these are available in one of my IEEE transaction industrial electronics papers. So if somebody is interested to look more in deep depth about these formulas, you can refer to that paper. And these are the generalized expressions. So this is what I was talking, since we have a fourth order converter. This is the generalized expression for the transfer function with s to the power 4, which says that our transfer function is of fourth order. And these are the coefficients which are derived. Some mathematical computation is needed, so you will obtain all these coefficients a0, a0, a1, a2, a3, a4 in terms of energy storage elements, load, and the duty ratio. This is for GVD. This is for GID. So similarly, if other transfer functions which are of interest can be found, but mainly for design, if you are going for a voltage mode controller design, only GVD is sufficient. If you go for current mode controller two loop design, then GID also becomes important. But as we have discussed the current dynamics also, I have included this GID as well. So this is the typical shape, which is again, this discussion is again going to be quite interesting. This is the shape of the frequency response of the control to output GVD transfer function, which shows that it has a couple of complex conjugate poles, and a complex conjugate zero and a real zero. So the placement of this on the frequency response, which is the Bode plot, is such that this forms two resonant peaks. So because of the presence of one complex conjugate pole, one peak arises here, and because of the presence of other pole, the next peak arises here. And this complete shape, so this complete thing is called as your up down glitch. So this is all placements, and this arrangement which is appearing is your up down glitch. So you can also find out by doing some mathematical analysis what will be the frequencies at which these poles and zeros will be placed, which will be helpful in further design. So one thing what you see is that this complex conjugate zero is placed in RHP or outside the unit circle if we talk of Z domain. As a result, your system is a non-minimum phase system, and you can see that there is a continuous fall of the phase, fall in the phase. If it would have been a non-minimum phase, a minimum phase system, this would have gone up. So this is one of the challenge while designing the controller for the converter. And second is because of the presence of this up down glitch, which depending on the location of these poles and zeros can sometimes be very tricky, and which will lead to unstable or conditionally stable systems. So you need to make up the things, you need to arrange the select the values of the inductors and capacitors in such a way that the conditional stability arising in the control loop can be stopped, can be omitted. So this up down glitch, its peak and its width depends on the frequencies and the dampings of these poles and zeros. So which is seen here that this is placed outside the unit circle, although these remaining are inside the unit circle. So this needs to be either shifted inside the unit circle if possible. If not, you need to make an arrangement such that the dampings can be changed and eventually that up down glitch can be minimized. Then in order to ensure that, and when the conditional instability, this is the frequency response of the loop gain. And here if you see that the magnitude plot is crossing this 0 dB line only once. There is only one crossing, rest all there is no crossing. So this is the ideal design that should take place, that this plot should cross only once. But just imagine if this curve moves little up, what will happen? If the curve moves up, this peak will also keep moving up, keep moving up, keep moving up. And there will be a point when there will be three crossovers, one here, one somewhere in this range which will come up here, and one in this. So this three multiple crossovers means it has three different cutoff crossover frequencies which will lead to conditionally stable system or sometimes unstable. Although for some of the particular load and source combination this may work fine, but you never know when this instability may arise for which load and source combination. And hence if the up down glitch is present and you are not able to completely omit this, minimize it, you need to place a safety margin of at least 6 dB such that the conditional instability is not arised. So this requires your placement of real zeros and this, so placed near each other. So these are the different combinations with for what I have discussed just now. And these are the, again, after performing some rigorous mathematical analysis, you can arrive at the frequencies at which the poles zeros are located and the dampings of those poles and zeros. And eventually you can find what are the different cases that when the frequencies are greater and less, what type of. So this basically is to show the different shapes of the up down glitch. You can see the shape is, it goes down then up then down. In this second case is it goes down then up and then down. In this third case is quite typical. So there can be several shapes of up down glitch that are possible depending on the frequencies at which they are located, the dampings, which ultimately depend on the magnitude of the energy storage elements, that is L and C. This was the third shape. So ultimately, these are the factors which we have discussed, that what factors affect the up down glitch. So damping and all. So ultimately what happens is RHP0 restricts the achievable bandwidth. If you have an RHP0, you will not be able to attain the bandwidth which is greater than the frequency at which the zero is placed. So this needs to be changed and the formation of up down glitch needs to be changed. So possible solutions are these. You can move them. Already we have discussed that we need to decrease the up down glitch, or you need to move the zero within the unit circle. So these are the generalized expressions. I think it is the repetition of the slide. So this is the condition. So using these expressions, you can derive the condition, that ultimately what condition you can place such that you can minimize the magnitude, but still you will have to ensure that the standards placed in the percentage allowable ripple needs to be met. You cannot overgo those standards just to attain the up down glitch or minimum up down glitch. So you need to take in mind that you do not violate any standard in the design. So this clearly shows us that further and mathematical analysis which makes it clear that the the relation is quite non-linear. You cannot simply say that if I increase L or a decrease LR, or I decrease C, I will be able to attain the thing. So I can increase it or decrease it. This won't work ultimately. So you need to go for some sort of, and all these are inversely related. So it makes quite cumbersome for manual design. So you need to go for some sort of optimization thing. So there are a lot of optimization techniques, although I will be talking of a very fundamental particle swarm optimization which I have used, but there can be many other techniques which can be used here to get even better results. So, but ultimately your low inductances are desirable, which we have been continuously talking about. So this is all mathematics that will eventually lead you that what can be done and what cannot be done, and these can be converted into either the constraints or your objective functions for implementing your optimization techniques for solving the problem. So this is the feasible solution, that you shift all this towards the right hand side. You change in the switching frequencies, increase in the switching frequency, and improves your frequency response. It also shifts your poles and zeros towards real axis, ultimately providing more damping. So this is by all this analysis we are able to form some of the basics that how we can optimize the thing. So these were the design parameters that are obtained for performing the experimentations, and these design issues to be addressed. So then with this sufficient mathematical understanding and the basics, we can form the optimization problem, which is formed something like this. These all we have discussed, what should be there and what should not be there. So this objective function is framed, which subject to the other constraints will be optimized using PSO. Most of you must be aware of this cognitive behavior, social behavior. So I think I should skip this PSO part because it may be known to you, and it's not related to power electronics as well. It's just implementation of PSO for power electronics. So I'll quickly skip up this. So you need to set up the local best, identify the local best population, then global best population. Then you need to vary the position, inertia, and velocity update. So the formula is available for updating. And finally, once you perform the design, you use these parameters in the design algorithm, and once you run the algorithm, the number of iterations you can in which it optimizes is 350 around, or in one case 700. And this is how the convergence of the initial particles take place. They cover the random space, and finally they settle at a final solution, which is shown here. We started with some initial, they moved around the search space, and they settled up here, in this case here and in this case here, after exploring the whole parameter space. And this is how the converters, all the parameters moved, and they landed up in some solution that if you particularly use these parameters, the uptown glitch can be minimized, or sometimes it can be fully neglected as well. So this is how the objective function varied, convergence of the objective function took place, and finally these parameters were obtained from the optimized design. And now if you see, the interesting solution appears that the frequency response plot shows that when if, with the PSO design, which is shown in the red color, the up down glitch is fully eliminated. Although there was an up down glitch which was present if you use the conventional design methodology, which is very popular. If you use that design methodology, you will end up in up down glitch. But if you go for an optimized design, PSO design, you are attaining very good results. This is for the second converter, where you see that a more dominating up down glitch is visible. But in this case, there is a very marginal up down glitch. On it should not be called an up down glitch. There is a marginal change in the gain, but that too it is at very high frequency, so it may not affect. This is for the third converter, which was having low source current ripple. So this was having up down glitch, but here it shifted to very high frequencies. So this is specifications for pole placement design that you can when once you want to go for the controller design. So once you have obtained the parameters, you go for the controller design. So you set up the requirement, that what are your requirements, controlling requirements. You set up with these requirements, obtain the controllers. So I have obtained the controllers for ripple based design as well as for PSO designed parameters for direct one-on-one comparison of the dynamic performance. So these are the comparison for the loop gains with and without PSO designs. So you can see that there is change in the bandwidth that is attainable. So in some cases this increase is marginal, but this is quite sufficient to increase the dynamic performance. So in almost all the three cases you see that the bandwidth has increased. So conclusions for this are, you have four fourth order boost converter topologies which were investigated. Low source current, load current ripple together with low inductance requirement. All higher order converters may not necessarily exhibit improved performance, and additional energy storage elements are there which may lead to the formation of up down glitch in the converter transfer functions, and which may lead to conditionally stable converter systems. So this optimized design needs to be there. And uh, so with this I would like to sum up what we have seen in the today's talk, is that the interfacing of the solar photovoltaic and a hybrid this wind turbine and the fuel cell is going to be the dead requirement for the coming future, and which needs technological development. And those technological developments mainly shall focus about different DC-DC converter topologies. That can be your single port or single input single output DC-DC converters, or those can also be the multi-port converter topologies, even the bidirectional higher order bidirectional. But the key is that all class of converters are available with minimum number of energy storage elements like your conventional. So you may be well aware of a conventional second order bidirectional DC-DC converter as well. But again, the challenges what we have talked are still valid for those converters as well. So eventually you need to increase the number of energy storage elements, and in some cases you may need to even increase the number of switches as well as the number of diodes. So the topologies can become complicated, but you need to always take into account that what is the trade-off in the design that you need to attain, whether your focus is on attaining the steady state requirements you are emphasizing, or you are also interested somewhat, you have some restrictions on the dynamic performances as well. So then you need to have a trade-off, the number of energy storage elements. So effectively designing a DC-DC converter or any power, in fact any power electronic converter, requires trade-off, because all there are multiple design requirements and they all are inversely related to, non-linearly related to each other. If you increase one thing, you compromise with the other. If you try to improve the one first, the third or the second will be uh, deteriorated. So that uh, thing needs to be kept in mind while designing. So higher order converters is always a solution for increasing, but that needs to be validated that how far it is serving your purpose. And these concept can be extended for multi-port converters, bidirectional converters, even the buck converters or the buck boost converters as well. So that's all from my side today. Thank you so much for being patient and attending and listening to the talk. Although it sometime, since it's a offline sort of interaction, I cannot see most of you. Uh, I hope you had find it a little bit interesting, and you find there is scope to uh, improve in these things. Okay, thank you.
Answer. Okay. So I think if anybody is having any question, please raise your hand so that Dr. A R Saxena will answer it. Okay, Manju Gupta ma'am is having some question, so I'm just unmuting him. Her.
Okay, sure.
Okay. Manju ma'am, I have unmuted you. Please ask the question.
I think it still shows are muted.
All are muted. It's only the Manju ma'am. Are you able to hear me? I have unmuted you. Please accept the request. Okay.
Hello, hello.
Yeah, hello.
सर इज इट हेलो हाँ अनमोल सर नमस्कार
नमस्कार मैडम, कैसे हैं
हाँ
आप?
सर बहुत अच्छे सर सर बहुत अच्छा लगा आपका प्रेजेंटेशन देखकर यू हैव गिवन वेरी नाइस प्रेजेंटेशन
Thank you,
एंड
thank
यू
you.
हैव इंक्लूडेड या यू हैव इंक्लूडेड लॉट मेनी थिंग्स complete converter design and all uh, a small question which I have in my mind we are using DC grid okay for the nano grid for the home purpose.
Okay.
So can we have any mechanism to just manage the DC and AC grid smartly, like some smart energy management system in this
Uh,
particular?
of course, ma'am, that can be added. That aspect, IoT aspects can always be integrated. So that will smartly manage your loads. I have not talked. If you see in the starting slide, I talked of the central controller. So in those
Yeah, yeah,
central controllers, we can still embed the maybe use through the CAN communications. We can still include your different sensors, and which depending on the sensing of your loads and the source
yeah.
availability can maybe control your switches, control your loads. So that possibility is always there, because ultimately you need to interface it with connect it with the internet and put some of the sensors. So putting it smart is always a solution.
Like at home, we use solar system and we use utility also, but sometimes we require to control. Means we have to shift from one source to another source immediately within no
Yeah,
time. If
yeah,
suppose
yeah.
solar is available, then go for the solar, and if it is in a less
Actually,
amount, then
yeah, I got your question. In that case, actually, there are some other DC-DC converters which are called as battery interfaced DC-DC converters. So in those converters, battery is embedded in between the load and the source in the same converter. Conventionally, what
okay,
we know is that we use a separate DC-DC converter, a bidirectional converter for interfacing the load and the source, load, source, and the battery. So in that case, if you see taking up of throwing from the switch to main source to the battery may sometime take time, although the time is quite negligible. We are already using those UPSs where in no time that switch takes place. But still there are some that integrated DC-DC converters, battery integrated converters, where for the time that transition is taking place, battery automatically takes up before the source goes out. So
okay, okay,
those class of converters fall under the category of multiple source converters, multiple port converters.
okay.
Those are the solutions for such things.
Means in future we want to shift the source from we want to shift the power from one source to the another source, and it should be done automatically, like we are designing the converters and all.
Yes.
So this is our future. Means we are going to add the IT solution in the this particular
Yeah,
nano
yeah,
grid,
yeah,
sir.
exactly, ma'am.
Yeah, yeah. So thank you so much to listen your nice presentation.
Thank
It's
you, ma'am.
really a
Thank you.
great privilege for us to listen you, sir.
Thank you so much, ma'am.
Thank you so much, sir. Thank you.
So if anybody is having a question, please raise the hand so that we can unmute you. I think so. Okay, I think there are no queries as
No.
of now. So I think thank you, Dr. A R Saxena, sir, for being with us and sparing your time to deliver this lecture. I hope all the participants have gained a lot from this session. And if they have any query in future, I will definitely route it to you so that you can
Yeah,
ask.
yeah, sure. Most welcome. And thank you to you, as well as to all the participants for patiently listening. Stay safe, stay home, And I think now mostly if it's working is started, so be at workplace, but follow all the precautions and be safe. Thank you, and thank you for listening.
Thank you, sir. Thank you, sir. Have a great day.
Thank you, same to you.